I've graded the prelims. I'll hand them back at the end of class. We'll end a couple minutes early for that. Stats are all over here. I don't know. That's a pretty typical spread, I guess, for a class like this. I think the exam was a little bit easier than the past year's prelims, and the mean was actually a little bit higher, which you'd expect if the exam was a little bit easier. But anyway, I usually aim for an exam for like a mean in the kind of 60s, so this is just slightly on the high end of that, but close enough. Anyway, I'm happy with this, and I'll hand them back at the end of class. I can say for each problem. Okay, by the way, this was so the 5670 exam had the same. It was a 4670 exam plus an extra problem, okay? And this is the average of all the 4670 students and the 5670 students with the last problem deleted. Okay, that's what this average is. I'm not going to put up separate statistics for the 5670 exam because there's only 3 people, and that's, that kind of violates privacy when you have the sample size that's too small, so we'll leave that up here. For the 4670 problems, for each problem, there was at least one student who got it completely right, but there was no student who got every problem right. There was one student who got very close, just missed one point on one problem. Anyway, so that's the prelim. So I'll hand that back. We have lab 3 due tomorrow. You can use a late for it if you want and turn it in Monday. I will post lab 4 pretty soon. That'll be due in at least a couple weeks. I haven't set the exact due date yet. There's a sizable jump from lab 3 to lab 4. Okay, lab 3 is a very controlled, contained channel. There's no synchronization issue. There's no question about what the channel is doing. It's right there in the script for you to inspect. So you don't have to try to learn the channel. We're not saying that many bits. The SVD works. Okay, so we go from lab 3 to lab 4. Lab 4 involves sending bits over the COM cloud. So then you've got all this stuff to deal with. So the jump from lab 3 to lab 4 is sizable. The jump from lab 4 to lab 5, I think, is honestly less big. So I intend to give quite a bit of time for lab 4. So I'll probably post that this weekend, and I haven't set the exact due date for that yet. Any questions? No? Okay, so we didn't quite finish the synchronization and system ID unit last lecture, so I'd like to finish that. That won't take very long, and then we can start talking about more advanced topics like coding. So let's recap where we were. So the channel model we're considering is the following. So the output is a vector. Think of it as a WAV file. The input is a vector. Think of it as a WAV file. And you construct the output from the input by taking the input WAV file, kind of prepending and appending a random number of zeros to it, passing that through your channel, adding noise, and that gives you Y. All right, and we're assuming that H is Toeplitz, but otherwise unknown. We're assuming the noise is IID Gaussian, and we don't know this number of zeros you got in the front and back. Okay. So when L1 and L2 were both 0 and H was known, we solved that problem, right? There's no synchronization problem, and H is known, then that's just communicating over a Toeplitz channel, and we have a method for that. That's OFDMs. We had a big block diagram for that. Okay. So we want to jump from that to the case where you don't know the number of zeros here, i.e. they're not synchronized a priori, the encoder and decoder, and also where the H matrix is unknown. Okay. So our solution is going to be to reduce this problem to that one. Okay, so the encoder is not really going to do much different from what we had in OFDM. There's with one exception that I'll explain. Most of the work's more at the decoder. Okay, so the decoder first of all is going to try to extract a set of samples from this Y that's as long as that X. I.e. it's going to try to figure out how many samples to delete on the front end and back end to reduce it to the synchronized case that we already solved. Okay, then it's going to try to learn what H is from the transmitted signal, okay, and then it's going to, then you just plug in that estimate of H in the previous system. Okay, so again, when H is known and when, you don't have these extra zeros here, we know how to solve the problem. So we're going to solve this case by figuring out how many zeros to drop on the front end, not zeros, but how many samples to drop at the front and back of Y, okay, to reduce it to the synchronized case, and then we'll try to learn H to then reduce it to the known channel case. Okay, and I talked about why these problems are hard and how they're intertwined and so on. I referred to this picture, which I think is a very useful picture to have in mind. Okay, so suppose you're sending just 2 OFDM symbols. Okay, so your transmitted signal, the X that the encoder forms would be a vector like this. You'd have a prefix of n plus samples, and then for each prefix, So an OFDM symbol consists of a prefix and then like a payload or a data block. Okay, the prefix is n plus samples. N plus is like the duration of the impulse response, and L is the number that you pick. Okay, so overall you're sending 2n plus 2L samples. The receive vector is going to be 2n plus 2L plus L1 plus L2. Okay, so the receive vector is longer. Okay, the decoder is going to decide to ignore a certain number of samples here, kind of roughly corresponding to this L0, L1 there, and a certain number of samples here, roughly corresponding to L2 here, and then just extract these samples and decode using that. Okay, and then when you decode, of course, you ignore the part corresponding to the cyclic prefix and just decode, the body, if you will. Okay, and then for the next OFDM symbol, you drop the prefix and decode from the body. So for each OFDM symbol, you drop the prefix and then decode from the rest. Okay, so we're going to extract this set of samples here. Okay, and the first question is, how do you choose which samples to save and which ones to ignore? Okay, the decoder doesn't see this whole picture, right? It just gets a vector of numbers. Okay, and it's got to draw a line, 2 lines, here and here, right? Now, it knows how many samples it should save. It's going to save 2n plus 2L samples. Okay, and we assume that these numbers are fixed. They're hard-coded in the encoder and decoder. So the decoder knows how long this transmission is. So it knows it should be saving 2n plus 2L samples. It knows how many samples it's got, obviously. It knows the sum of all these things. Okay, so obviously, if once you pick this number, you've also picked this number, right? Because this plus 2n plus 2L has to equal the total number of samples you've got. Okay, so really you're just picking one number. Like you're kind of picking where to cut it off right here. Okay, and once you've done that, then that also dictates which samples get dropped here. Okay, so first order of business for the decoder is to decide how many samples to drop off the top of the signal, off the front of the signal. Okay, and we noted last time that the effective H matrix you get depends on that choice. Okay, so if you extract these samples, okay, and then just view the channel as mapping this input here, call this X, this input to that output, okay, then your overall channel looks like this, okay, where H is toplets. And the point is this H matrix that's multiplying the X depends on where you start. Okay, so pictorially, this H matrix here corresponds to this middle right here. Okay, so what appears in the orange square, okay, is going to depend on where I draw this line. Okay, if I trigger early, if I trigger up here, the whole orange box is going to move up like that. Okay, in which case these non-zero values will kind of sink low. And if I trigger late, okay, then the orange box is going to slide down on these two rails here, this rail, okay, and then the band is going to kind of move up inside the window. So if you just think if this is a window and you look into it, okay, if you trigger late, okay, this band will appear high in the window, and if you trigger early, this band will appear low in the window. Okay, and we talked about the problems with both of those extremes. Okay, if you trigger too early, you have, let's do the other way first. Actually, if you trigger too late, okay, the orange box is low. Then you have an H matrix that's not lower triangular, so it's not causal. Okay, and so then the cyclic prefix is not going to be enough to turn Toeplitz matrix multiplication into circulant matrix multiplication. Okay, you would need a cyclic postfix as well, which we didn't do. Okay, so you want to choose this point here so that your orange square is such that you get a lower triangular matrix. And then if you trigger too high or trigger too early, the orange thing would slide up. This band would slide lower. Okay, it'd still be causal. Okay, but you just have a large delay in your system. The channel would have a large delay before it starts responding. Okay, and your n plus has got to incorporate that. So that works so long as n plus is chosen to be big enough. Okay, but if you fix n plus to be like the actual duration of the impulse response without any artificial delay added in, okay, and then trigger too early, okay, then this is not going to be a sufficient guard band to protect the two intervals from each other, and they'll crash into each other. Okay. Okay, so bottom line is you want to choose this point here, i.e. you want to choose the number of samples you drop here so that the matrix you get is lower triangular, but the band is as close to hugging the diagonal as you can make it. That's what you want to aim for. Now, of course, the decoder can't see this orange square. It just has a vector of numbers. Okay, so it's got to look at that vector of numbers and try to decide where to draw this line so that if a genie who had all this information drew the picture, the square would end up looking like that. Okay. We talked last time about how to do that. We With low SNR channels, that can be a very challenging task. Our channel is very high SNR, however. So there's kind of a simple way of achieving this, which is just look for the power to spike up. Okay, so what will happen is these early samples, they're just going to be noise, right? Like, take this sample here, right? That's multiplying like this. Okay, so all of these non-zero values in the impulse response, they all get multiplied by zeros here, right? So you have just noise. Okay, so it's like you have just noise, all noise, pure noise up to a point. Okay, and then right at this point that you want, these samples start being actually influenced by the signal. You actually get like non-zero value here times non-zero value here. Okay, and that contributes to the signal along with the noise. So we just want to find the sample where you start seeing energy from the signal. Okay, one way of doing that is just look at like the moving average of the power. Okay, so just to find some signal to be like the locally averaged power level. Okay, and then just trigger that. So just wait for that to exceed a threshold. Excuse me, and then call that L1 hat. And we talked about why you might want to average this over several samples so it doesn't trigger spontaneously too early. If you do average it, you probably want to back up your estimate a bit because it'd be a bit slow to respond. And that's that. Okay, so if you do that, then the decoder knows how many samples to delete on either side here. Okay, and then you have y that's the same dimension as x. Okay, so it matches the problem we solved earlier. The only problem is, your matrix looks like this, but you don't really know what these values are in here. You can't predict them ahead of time. Okay, so the simplest way around that is to have the first OFDM symbol not send data. Okay, just fix the frequency coefficients of that first OFDM symbol to be numbers that are just hard-coded in both the encoder and the decoder. Okay, so RK, theta k, okay, these would be numbers you just hard-code in the encoder and the decoder. All right, so the first OFDM symbol would always be the same regardless of what data you're sending. All zeros, all ones, random, doesn't matter. Okay, this OFDM symbol would always be the same. It'd always be those coefficients. Okay, and then the decoder, it'll measure frequency responses. In the frequency domain, while have some values for these different frequencies. So if you want the gain of the system at these different frequencies, okay, you can just take the output gain at that frequency or the output amplitude of that frequency divided by the input of that frequency, and then use that as your channel estimate. Okay, and then at that point just delete this and don't worry about it anymore. Use that estimate to then decode all the following OFDM symbols, and just like in the known channel case, and that's that. I'll point out one somewhat subtle point here. So another way you could do this would be to just the beginning of the transmission, don't have it be OFDM, just send an impulse right at the beginning. Just send a 1 followed by a bunch of zeros. Okay, and then trigger on that impulse response. Okay, measure the impulse response, take the DFT of it, and then use that to estimate the gain and the phase shift at all of these frequencies. Okay, that works. Okay, not quite as well as this in practice. Okay, in my experience. Okay, and my own theory is the reason is that it doesn't quite work as well as this is that like ultimately you're encoding bits in the frequency domain, right? So what you really care about is like when I input a particular number on a particular frequency coefficient in the input OFDM symbol, what gain does it experience when it gets mapped to the output OFDM symbol over here, right? If the system is linear, exactly linear, and exactly time invariant, okay, then in principle the frequency response is exactly the DFT of the impulse response. Okay, and so if you have the impulse response, you can take the DFT, get the frequency gains, and you're done. Okay, in practice the channel is not exactly linear. Okay, and it's not exactly time invariant, and you've got noise in here too. Okay, and so rather than measuring the impulse response and taking the DFT and relying on the fact that in theory, okay, the DFT of the impulse response should be the frequency gains, which is what you really want, why not just measure the frequency gains themselves, right? And don't rely on anything fancy. Just measure exactly the thing you care about, not some indirect thing, and then try to convert it. Okay. So once you have an estimate of the channel, you can decode subsequent OFDM symbols, only up to a point though. Okay, so as you wait longer and longer, your channel estimate gets worse and worse. Okay, and eventually it's not good enough anymore. So in practice, you typically send a bunch of OFDM symbols and then just like retrain. Okay, so So I'll say retrain and resync as needed. Okay, so then the transmitted signal would look like the following. So there's nothing. Okay, and then you're going to send one OFDM symbol which has a prefix and then training. So no actual data. So if you just if you were to plot the input signal in MATLAB and zoom way out, kind of the envelope would sort of look like this. It would kind of go from just not zero signal to an amplitude. Okay, and the first little bit would be the prefix for the training. Maybe I should color code this actually. That would be a lot clearer. Grab some colors while I'm over here. Okay. Okay, so it's going to send a prefix. And then the training. Okay, and then it'll send OFDM symbols with data in them. So a prefix and then data. And then a prefix and then data. These are supposed to be the same size. Okay, and so on. Okay. So blue is data. Okay, so now at the decoder, okay, so the decoder first of all has to figure out where the transmission starts. So it's going to use this power level test right here to kind of find the start of the transmission. So I'll say use measured power. To identify this spot at the receiver. Okay, so it's going to trigger on the power rise that happens right around there. Okay, it then just paces off. Okay, so the length of the prefix, the n plus, you hard code that in both the encoder and the decoder. The decoder knows how long this first prefix is. So it just paces this off. It's 100 samples. It just paces off 100 samples. Okay, and then just drops those. All right. It then knows how big this part is, the training portion of the first OFDM symbol. Okay, so if that's, 500 samples, okay, it paces off 500 samples. Pull those out, take DFT, drop DC, drop redundant second half, and so on. Use that to estimate the channel. Okay, so estimate channel. Okay, and then now you're here. Again, you know how long the prefix is, so paste that off, drop it. You know how long this data portion is, so paste that off, peel it out, okay, take the DFT, right, drop the redundant second half of the spectrum, drop the DC and so on, and then decode bits. And then just repeat. Okay, so now you're here, paste this off, ignore it, paste off this portion, extract it, decode, keep doing that, okay? All right, so when do you stop? So there's sort of two stopping criteria here. One is you just run out of bits. Okay, so if your entire transmission, can fit in a little, if all your bits can fit in a transmission like this, then you're golden. Okay, it can happen though that by the time you get way out here, like suppose you want to send all your bits, you just keep sending more and more OFDM symbols, okay, until all the bits get through. Okay, the problem is I learned the channel here, right? So I had a pretty good estimate of the channel as of this time, right? But the channel's time varying, right? So as time elapses, it starts drifting. Okay, and with each subsequent OFDM symbol, the actual channel deviates more and more from my estimate that I obtained over here. Okay, so the various ways around this, we'll talk about sophisticated ways of handling this shortly. Okay, but a sort of quick and dirty way of dealing with this is just to stop this transmission at some point when the channel estimate gets to be too far from reality, and just start over again. So just have the encoder send a bunch of silence, and then just repeat this whole thing over again. So send a whole new train of OFDM symbols with prefixes and with data. So, sorry, with training. So again, the first OFDM symbol is training. And then after that, there's data. And then just repeat that as many times as needed. So you decide how many symbols you can fit in here. Maybe you can fit 10 or something. You send 10 OFDM symbols, and then silence, and then 10 more symbols. The first one being training, silence, 10 more symbols. You can do that indefinitely. Okay. And one really important point here: the decoder, it triggers on this spot from the power increase, right? It then paces these off to identify what's the prefix, I'm not sure what to call this part. I don't know if there's a term for this thing. OFDM symbol is the whole thing, and that's the prefix. But what's this? Body, payload, data, I don't know. This part, okay? It paces off the payload, it paces off this part, it paces off the prefix, paces off this part, paces off prefix, and so on. Okay, by the time you get to here, okay, the decoder will probably know, you could in principle hard code this distance here, but don't paste this off, okay? Instead, just repeat like you did here. Just find this start time here from the rise in power, okay, resync. Right there, learn the channel from here, and then keep going. You just forget about all this when you go to decode this one. And don't try to coordinate these two. Okay, so it uses the measured power to identify this spot and here too. Okay. The reason why it's important to not try to paste this off from its distance, like at the encoder, this point will be a fixed number of samples from this one. Okay, so it's tempting at the decoder to say, well, I know where this point is, so let me just paste off that many samples and get to here. Okay, the point is that the channels don't stay in sync, right? One clock is advancing faster than the other. So they might start out in sync here, but then their synchronization diverges over time, okay? Until by the time you get way out here, one is a sample ahead or a sample behind. And if you just try to pace off, okay, then that divergence just accumulates. So rather than allowing that to happen, just start over, resync here. Now they're freshly synchronized, and keep going. Yes?
Yeah, I'm a little bit confused as to how we decide what n plus is about the channel.
Okay, good question. So n plus, we said, is governed by the duration of the impulse response, right? So yeah, you need some kind of knowledge about the duration of the impulse response in order to pick that. That's true. You can't just fly completely blind, okay? At least in our system with no feedback. So ComCloud's completely feed forward, right? So you send the signal through, and there's no way for the decoder to send information to the encoder, right? At least on one run. Now, most real-world communication systems, or many at least, have feedback. We actually send information bidirectionally, right? So, if you really were in a situation where you had no idea whatsoever what the duration of the impulse response was, you could imagine some protocol where you kind of send some probing signals, using a really, really conservative estimate for n plus, okay, and the decoder then tries to estimate n plus and sends that back, and then you kind of refine your estimate and so on. In practice, people don't really tend to do that, even when they have feedback links. You just, choose some n plus that seems, n plus only needs to be longer than the impulse response, right? It doesn't have to be exactly equal to the impulse response. It has to be longer than it. Okay, so in practice, you just choose some n plus that's guaranteed to be longer than your impulse response, and that's it. So for ComCloud, you don't know exactly what the impulse response is going to be. It depends on how the samples between the encoder and decoder line up and stuff. But you give the duration of it in samples is pretty consistent run to run, right? So that you can kind of measure offline and just hard code that in your encoder. In Wi-Fi, for instance, we'll talk about wireless and Wi-Fi standard later. Wi-Fi uses OFDM. So they just did experiments in buildings, okay, where they just sent probing signals around and looked at how long it took for the channel to die out, and then they came up with an estimate of how long that was, and hard coded that as a number in the standard. Okay, so it just uses one number, which is presumably going to be longer than the impulse response that you've got, whatever that is. Okay, it's potentially inefficient in that if your impulse response is a lot shorter than that, then it's using a lot more prefix than it needs, okay, which is wasteful. All that's all dead time, right? Dead time, right? The only data is here, 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 okay? So the longer your prefix is, the more time you're wasting, but the safer you are and the less likely you are to have these things crashing into each other. Yeah, other questions? Okay, so speaking of dead time, there's kind of an optimization problem lurking here in that, like, you know, the duration of this is kind of determined by your channel, right? You don't get to play with that too much. This duration is also determined by your channel, right? How long you can go until you resync. Okay, that's governed by how long the channel remains constant before it starts changing on you, right? So this distance here is sort of fixed by the channel. This distance here is fixed by the channel. I get to pick this one, though. Okay, and the larger I choose this to be, the fewer symbols I'm going to have. The smaller I choose this blue thing, you know, the more symbols I'm going to have. Okay, and both extremes are inefficient. If I choose the payload part to be really small, okay, I'm going to have a lot of OFDM symbols, but each one has this big prefix in it, right? So you have a lot of wasted time through the prefix. If you go the other direction and choose each OFDM symbol to be really big with a tiny prefix and a big payload, okay, what will happen in the extreme case, you'll have two OFDM symbols. You have one big training one and then one data one. And so the training just ate up half your time, right? Whereas, you know, if I do it this way, you know, the training only comprises one out of a bunch of symbols. Okay, so like too small or too big are both kind of bad. You got to find the happy medium here, which is some calculus problem you can solve as a function of this amount of time and then that amount of time. Okay. One other point about this. I tried to make this point last time, but I think without this picture it wasn't very clear. So let me try again. So. Okay, so the decoder is going to like trigger on this spot, just looking for the power increase, right? And then it's going to start pacing off. It knows how many samples are here, how many samples are here, and so on. So it divides this up and then treats each piece separately, right? Okay, so in particular, you know, it'll identify this spot, pace off this prefix, pace off this training piece, and then learn the channel from this, right? Okay, now suppose you decide to trigger, suppose the received waveform is fixed. Okay, so you have one received wave file you're playing with. Suppose you decide to just trigger one sample early. Okay, so just trigger one sample earlier than you did the first time through. Okay, so when you go to pace everything off, everything's going to be kind of one sample shifted from what you had before, right? Because you're going to say the transmission started one sample earlier, so the prefix started one sample earlier, so it ended one sample earlier. This training part's one sample earlier. Everything's one sample earlier. Okay. When you go to learn the channel from this piece, using this right here. Okay, when you advance this by one sample, you're going to get rather different numbers for these phases, especially at high frequency. Okay, you know, one sample, you're essentially adding like a one sample delay to the channel when you trigger one sample early. Okay, and one sample can comprise a rather large phase shift at high frequency. Okay, so you know, a lot of students will see this and they'll sort of express dismay that this is happening. You know, like why, I mean, especially because you can't really identify the start of the transmission, like you can't pinpoint it to one sample anyway, as we discussed last time. Like it has kind of a soft start, right? So there isn't really like one sample you can say that is the start of the transmission. There's like a handful of them, any one of which are like reasonable guesses for where the thing started. So it seems kind of weird that like, you know, your estimate of the channel, which seems really important, it's kind of weird for that to be such a sensitive function of the choice of where you trigger here, especially when there's no one right answer to that. Like plus or minus one sample are all reasonable guesses, and yet they give you like radically different phases over here. Turns out that's not a problem. Okay, it might seem kind of unnatural, okay, but it's actually not a problem. Do you see why it's not a problem? Yeah. You are going to cancel the phase out at the decoder. That's true. But like, it sounds like I really have like a great deal of uncertainty about what the phase is, right? I mean, I just trigger one sample plus or minus, and I get like this radically different phase. So how can I cancel it when I don't know what it is? My estimate changes so radically. How can I cancel something that I don't know very well? That's the source of the fallacy. But actually, this is not a fallacy. There's really no problem here. I'm just going to erase while we think. So ultimately, the channel estimate I get from that first OFDM symbol, I'm going to use that to decode the subsequent OFDM symbols, right? Okay, so now suppose I just trigger one sample early. I've effectively just shifted this thing, this matrix, the orange square, I've shifted up by one sample. It's like delaying the impulse response by one sample. Okay, so all my phases change. So my estimate is now quite a bit different. Does it affect my decoding of these? Does it harm my decoding of these? And why not? No dice, huh? I'm trying to think of clues that I can give to kind of move this along. It's kind of a subtle point. I'll just tell you what I'm thinking because it's kind of hard to it's kind of hard to kind of lead the discussion where I'm trying to go. So, okay, suppose you trigger one sample early, right? So then when you go to pace all this off, everything ends up being one sample earlier than it was before, right? So in particular, this part was one sample. You think this part's one sample earlier than you had before. Therefore, you get different phases from what you had before, right? Now, when you go to decode this, you've also triggered one sample early on this. So this is now earlier than one sample than you had before. Therefore, the channel that this block experiences has that phase shift that you just experienced. So does this one, and so does this one. Okay? The point is that the channel matrix is not like this fixed entity of which it's not this immutable thing of which there's one right answer and you've got to figure it out. The channel matrix depends on where you trigger. If you trigger plus a sample, minus a sample, that would change the H that you've got, but it changes the H for all of these symbols, not just this one. Because they're all tied together, they're all being paced off from this one common starting point. So if you trigger a sample early, it changes H for all of these, not just this one. And yes, the phase will change, potentially a lot, but it changes for all of them at the same time, not just this one. That's why it's not a problem. Okay, as long as the phase you measure here is the phase you experience here, you're fine. Where you get in trouble is where the phase you measure here is not the phase experienced here. That would cause a problem. But if you just trigger one sample early, you're changing the phase all the way through, and that's not a problem. People with me? Yeah?
So that makes sense, but if you trigger a sample early,
Yeah.
since you kind of pace like you kind of samples to figure out the prefix and then the training and the prefix data, wouldn't you throw out a sample at the end of your training?
So, okay. So this is like the transmitted signal. Okay, when you pass it through the channel, it's not going to have this crisp start and end to it. Okay, it's going to kind of go up like that, and then kind of go down like that. Okay, and the point is it has kind of a soft start and end. So another way of looking at it is that when I draw this here, it's like there's this crisp delineation between the non-zero values and the zero values. Okay, when in reality the soft start means that the first non-zero values are very small. Okay, and so we say we want this band to be below the diagonal, but as close to the diagonal as possible. But in practice, that's kind of hard to pin down what that means exactly because it has such a fuzzy start to it. Okay, so when you kind of advance one sample or delay one sample, you're kind of just coming up with different solutions to the problem of kind of identifying where the start of this thing was. Now, if you go way too far, then the problem you're describing can happen, but that just basically maps to having a channel where this thing is substantially non-causal. Like if the band ends up way up in here, okay, or way down here, then if assuming the n plus is fixed, okay, then you've kind of missed part of the transmission. But as long as it's kind of in this vicinity here, you're going to capture the whole transmission. It's just a question of where what you call the start of it. Yeah. Yeah. Other questions? Okay. So with that, you can design a reasonable system for CommCloud. In fact, you have everything you need now to do Lab 4. Okay. This is a good basic system. There are various improvements you can do to this to get improved performance, however. So I'll list a few now. Some of these we'll kind of dig into rather deeply, some we won't. Let's start with an easy one. Okay, so move training the middle of the block. Let me try again with asking a question. This one's easier, I think. So why would moving the training to the middle be better? Yeah. Why would I need one fewer prefix? You actually do need prefix for the training. Actually, that's an important point. So the training, you want the training, because ultimately you're trying to figure out what frequency gain the frequency coefficients in these symbols will experience. Okay, so the best way of determining that, okay, is just send a symbol that's as like these data symbols in every way possible, except rather than varying the frequency coefficients with the data, with the bits, you just hard code the frequency coefficients. Okay, and then you use that information to then estimate the channel. But you want this thing to resemble these as much as possible so that the frequency gain you measure here matches what's experienced here. Yeah. Other suggestions? Yeah.
Because like it minimizes the error, so like the last data thing has a lot more error.
Yeah.
The channel is like varying, and if you put it in the middle, it's like the equalizer from both.
Exactly. Yeah. So so if you have to decode each OFDM sample as it comes in, like we're trying to do this in real time, then it makes sense to put the training here, okay? Because then as moment this symbol comes in, you can decode it. Then this one and so on. You can decode each one as they come in. Okay. For CommCloud, we're not doing this real time. Okay. You import this entire signal into MATLAB and then decode the whole thing offline, right? So you can put the training wherever you want. You can put it at the end. Okay. You can put it at the beginning. You can put it in the middle. Okay. If you put it in the beginning, okay, then the issue is the training. You know the channel quite well right here, but then over time the channel drifts on you, right? Okay, and so your channel estimate's a little bit inaccurate here, a little bit more inaccurate here, and so on. It gets more and more inaccurate until eventually it's so inaccurate, okay, you got to start over. Resync, retrain, start over, okay? And what governs this is like the time variation of the channel and how long you can wait until your channel estimate is so bad you start picking up a lot of bit errors in this OFDM symbol. Okay, so one like really super easy way, okay, of improving this design is just move, assuming you can do this off, you're not decoding in real time, move the training to the middle, okay, and then no one OFDM symbol is as far from the training as it is here. Okay, so that's easy. Question? Okay, another idea is to combine training and the data symbols. Okay, so the way I describe this, you have, for each OFDM symbol, you're either sending no data, just pure training, okay, or sending all data, like there's no training, right? Okay, but in reality, you don't have to divide it up like that. In particular, like, consider this training symbol here. The way I described it, for each frequency component, okay, rather than saying a bit, you lock that component to some pre-specified value. Okay, and the decoder estimates that frequency component using this equation. Okay, but the channel gain is going to be kind of similar for nearby components, like for neighboring components. Okay, so you could, in principle, like send training on all the like even numbered frequency coefficients, send data on all the odd ones. Okay, and then estimate the channel for all the even coefficients using this, then just interpolate over the odd ones, and that's almost as good as estimating each one separately. Moreover, okay, I mean, you could, if you wanted to, you could put multiple training here. You could have training, some data, more training before you resync. Okay. Another option yet, okay, is do a really thorough training here, okay, and then do like touch-up training later, where maybe one of these OFDM symbols has not all data in it, but some of the frequency components are specified to be training. Okay, and the decoder updates its channel estimate using those frequency coefficients in this sample here. Of course, the decoder has to know which symbols got that and where they are and so on, so you have to hard code that. But but you could do that. Okay, another more, even more sophisticated idea. So update the channel estimate. As you go, as the decoder goes. Okay, so here's what I mean by that. Okay, so decoder finds the start of the transmission from just power considerations, right? It learns the channel from this. Okay, it then decodes this OFDM symbol, right? So it gets bits here. Once it has bits, it can emulate the encoder and figure out what the transmitted symbol was here, right? Once it thinks it knows what the bits are, okay, it can just like run the encoder algorithm itself and then figure out what this OFDM symbol was on the transmit side. Once it knows what the OFDM symbol was on the transmit side, it can actually, and it knows this symbol on the receive side, it can divide the two again to get another estimate of the channel, right? Okay, and that estimate would be fresher than this one, okay, because it's more recent. And then you can keep going, right? So now decode this one using the channel estimate you got here. And once you've got the bits, figure out what the transmitted signal was here, divide it to get a channel estimate for this, and then keep going. Okay? You can kind of track the channel that way. So as the channel changes, you're actually changing your estimate along with it. There are obvious concerns here about like propagating errors. Okay, if you decode some bits wrong here, okay, then you're going to update your channel estimate in a bad way. That's going to make you more likely to make errors here, and the whole thing can kind of catastrophically collapse. Okay, so that's a concern you got to keep in mind. In practice, it's usually possible to do this in a way that kind of mitigates that possibility. You can even do like a moving average thing, right? So you can put an estimate for each OFDM symbol as you decode it. Okay, and then rather than taking just the most recent one, do some kind of moving average of them that can help with the error propagation. You can even, if you want to get fancy, you can sort of predict what the channel is going to be for the next block. Okay, so like I decode this block, this OFDM symbol. I estimate the channel from it. Not that I decode. I mean, the frequency components are like hard fixed, hard coded here. So I estimate the channel from here. I then decode this block. I get an estimate of the channel. I now have two estimates of the channel, right? So I can extrapolate from these two and figure out what the channel is going to be here, right? And then keep going with this over time. Okay, and that tends to work very well, especially for the comm cloud, because the source of the channel variation for us is just the clock drift. One clock is advancing faster than the other. Okay, so the phase shift imparted on a particular frequency, okay, it's going to start at one point and it's going to kind of drift one way or the other, depending on which clock is advancing faster. Okay, so as you do this, if you really want to get fancy, you can actually estimate the speed with which this phase is changing from block to block. Okay, and then as you move along, you just kind of adjust your phase estimate in accordance with that. Okay, and if you want to get really, really fancy, okay, you can estimate actually which clock is going faster between the two. Okay, and then rather than just resyncing like this, you can have the decoder at the appropriate time either advance a sample or delay a sample to compensate for the clock skew, and then just keep going. So you can actually eliminate this whole silence piece here, okay, if you go nuts with this idea. Okay, that's another idea. Did you have a question?
Yeah, so this is the basis for like convolutional codes and stuff like that for error correction. How similar is this to like injecting?
I would describe this as different. We're actually going to talk about error correction starting right now after I finish this, because in error correction, conventional error correction, you assume you know what the channel is, and you're just trying to kind of undo the damage that it's doing. Like you know its statistics. And you're just trying to undo the stochasticity of the channel. Here, the issue is like we don't really know what the channel distribution is. I mean, you don't really know what, like y equals hx plus z, and we don't really know what h is. So we're trying to learn h as we go. Error correction, at least conventional error correction, helps you when you know what h is, but you're trying to kind of overcome the effect of the z. Yeah. Other questions? Okay, some other ideas. I think we're probably good to erase this now. Okay, you can do Bayesian estimation of the channel. Okay, so remember estimation from way back when? So we talked about inference. We said inference has two parts. There's detection and there's estimation, right? And detection is where you're trying to guess a discrete quantity and you're trying to guess it exactly. Estimation is where you're trying to approximately guess a continuous quantity, right? We spent a lot of time on detection because that's the problem that arises most frequently in digital communication. You have bits, so you have a bit string, and you're trying to detect what the bit string is, okay? Learning the channel you can view as an estimation problem. Okay, you have continuous parameters you're trying to learn. Maybe I should call this a hat here. This is not the exact channel. This is like an estimate of the channel, right? Okay, you have a channel that has continuous parameters. You can't learn them exactly. You're trying to learn them approximately. You're trying to infer these from data, right? That is an estimation problem. Okay, you can put that in the framework that we, a similar framework to what we studied in our detection unit. What you'll find if you go through all that math, we don't really cover that math in this class. If you do go through it, in the really high SNR case, okay, then like the optimum estimate is just going to be this ratio, okay? But for people who are taking 4110, okay, you'll know that in the low SNR regime, this is actually not the best estimate. You can come up with a better estimate for this thing from this data beyond just taking a simple ratio like this, okay? So if you're dealing with low SNR channels, okay, there are better ways of guessing the channel than just taking this ratio. So I want to mention that here, but for the COM cloud, the SNR is high enough that that doesn't really buy you a whole lot. What else? I had a list here. Okay. I'll say send. So send a special signal to mark the start of the transmission. Okay, namely, there are more intelligent ways of helping the decoder find the start of the transmission than just relying on this power thing. If you have a very high SNR channel, as we do, the power thing works well enough. And it's simple, so just stick with it. Okay, the issue is if the channel is low SNR, okay, then just watching the power envelope of the received signal is not enough to really find the transmission. Like if you're, I don't know, if you're NASA, okay, and you're trying to communicate with some probe out in Saturn, okay, the received power level is going to be buried in the noise, right? So you can't expect that when the transmission starts, suddenly the received power will shoot up. Okay, just the noise, the received signal just looks like constant amplitude because it's just buried in the noise, right? So you can't rely on this kind of envelope trigger thing to find the start of it. So what can you do? You can send an impulse, but then it's like the decoder has to know what the impulse response is in order to look for that pattern. And you don't know what the impulse response is necessarily if you have a lot of ISI. So people have developed some pretty clever schemes for this. So one thing you do, for instance, is you have a particular signal and you send it twice back to back, like this, okay? And that passes through the channel. The channel, convolves both of those with its impulse response, okay? At the decoder side, it doesn't know what the received signal is going to look like, but it knows it's going to be something, and then that something again, right? Because you have like the same signal kind of back to back, and so when the channel convolves it, you get the thing convolved with the impulse response, and then the thing convolved with the impulse response again, kind of back to back. So what we can do then is just kind of like correlate the received signal with a delayed version of itself, and look for a spot in the signal where you have like two pieces that look similar to each other but are delayed by a certain known amount, and use that to mark the start of the transmission. Okay, so it's pretty clever. That works pretty well. And at low SNR, you got to do something like that. At high SNR, it's fine to just do this. But I'll mention that as a potential improvement. And then I'll mention peak to mean power reduction. Okay, so we haven't talked about this concept at all yet in this class. OFDM signals tend to have a high peak to mean power ratio, or maybe I should say power ratio reduction. Okay, OFDM signals tend to be peaky, okay, because like you encode the data in the frequency domain. So in the frequency domain, it tends to look kind of flat. So when you take the IDFT, you tend to get kind of peaky things, okay? In a theory class like this, like a signals class like this, it's like we don't care. Just encode the bits how you want. Take IDFT, send it, good. Okay, if if you're responsible for designing the analog circuits to this thing, okay, then you really appreciate if the signal is not so peaky, okay, because it's hard to design amplifiers that are linear when they have to be linear. They're typically sending very low amplitudes, but then occasionally they send these huge amplitudes, and so you need the thing to be kind of linear over this big range. Okay, so people have devised ways of tweaking the design a bit so that the time domain signal that you get doesn't tend to have these huge peaks in it. And yeah, so anyway, that's that point. And then the last point that I'll mention is better mapping of bits to frequency coefficients. Okay, so right now we're mapping bits to the frequency coefficients just using like PAM in each dimension. Real part, imaginary part. You just encode the bits using PAM. So you have these square constellations, right? It's like a square grid, and you just encode the bits, to those points. Okay, that is not necessarily the best way of encoding bits in the frequency components. It's simple, okay? It's convenient. Okay, it's not necessarily the best from a performance standpoint. Okay. All right, so the various improvements one can make. Some of these, I think, conceptually, I think there's not a whole lot. I've said everything I can say, and that's pretty cut and dry, I think. This, I don't have much to say about it. You just kind of experiment with different designs, see what works well. Likewise with this, I don't have a lot of theory. This is not useful to us. This is not useful to us. We will talk a little bit about this. Probably this one, I'm guessing Umair will talk about in a future recitation. I will talk about this for actually several lectures starting right now, and also tomorrow's discussion will also touch on this a bit. So for Lab 4, you don't need this. Lab 4, we're just going to use the design kind of as given with on-off keying in each frequency component. Okay, so the mapping of bits to frequency components is very simple in Lab 4. Lab 5, though, one of the goals will be to design a system that just high performance as you can make it. Okay, so for Lab 5, these kinds of improvements are useful. Okay, so tomorrow's recitation, Umair will talk about some of these ideas here, and I will talk about them starting right now. Any questions on all these improvements around the design? Yeah.
What's the general idea behind peak to mean power ratio?
So if you just implement the design as we've described it, you tend to get peaky signals. Okay, you tend to get time domain signals that kind of hover around 0 and then have these very large peaks. Okay, that is undesirable from an analog circuits standpoint. Okay, as far as this class is concerned, we don't care. It's a signal, it satisfies the power constraint, good enough. Okay, but when you go design the DAC and the amplifiers and stuff, that creates trouble. Okay, so and actually, it can create a little bit of trouble in this class in that you can get clipping. Okay, so it can happen that when you go to do like Lab 4 or something, you implement this design and you take the inverse DFT to get your time domain signal, and you've got your X all set, your X vector all set. You go to write to a wave file and it clips. Okay, because the amplitude's bigger than 1 or below -1. Okay, so I guess it can cause trouble in this class only because the wave file clips things to be -1, 1. Okay, so the improvement is just like what I'm referring to in point 6 is like a whole suite of techniques, okay, that one can use to tweak the design so that the time domain signals that you get are not quite so peaky. All right, other questions? Okay, so this is an important waypoint for the class. So we have a basic design that works, and you have everything you need for Lab 4. So the remainder of the class, we have 9 point something lectures left. So the remainder of the class has 2 parts to it. we're going to talk about certain improvements to this design, especially how to better map bits to frequency coefficients. This is where error correction comes in. Okay, and then we'll talk about wireless also and how everything we learned here maps to wireless, like Wi-Fi and cellular and so on. Okay, so we'll do a few lectures of this, a few lectures of wireless, and then that's it. Okay. Okay, so we're going to switch gears now. We won't have a whole lot of time to do this lecture, but I'll start it. We'll pick it up on Tuesday. So we're going to switch gears now in that, we have a basic design, and we're not trying to add in a new element to make this design work in practice. We're actually kind of improving the design and making it more sophisticated and perform better. Okay, so how to map bits to frequency coefficients. That's what I'll call coding. Okay, so first, high-level statement. So the mantra up to this point in this class has been keep separate bits separate, right? We want to avoid ISI, right? The channels with ISI tend to blend samples together, and so if you encode bits in these different samples, the channel smears them all together, and it's hard to extract it. So we don't want that, right? So we go through all this work, i.e. OFDM, et cetera, okay, to encode the bits in such a way that they don't intermingle with each other as they pass through the channel, and it's a lot easier to decode them. Right? That's been, our mantra up to this point. Okay, the justification for doing that, for keeping the bits separate, was always one of convenience. Okay, I never argued it was optimal to keep the separate bits separate. I always said it was inconvenient for the channel to have the channel mix them together, because then you've got to try to disentangle all that. So it's a lot more convenient if we keep them separate. Okay, and I was careful how I phrased that, because it turns out it's not optimal to do it that way, to try to keep all these bits separate. It's convenient, it's not necessarily optimal. To achieve really good performance, you've got to mix bits, actually. So now we're going to talk about how to mix bits. Encoding, in my mind, is basically a study of how you mix bits. Okay. Now my seems like we're going around in circles here. Okay, we just spent how many months? A good 2 months talking about how to prevent bits from getting mixed up together, and now suddenly we want to mix them. It's why did we go through all this to begin with? We just let the channel mix. It seems like we're kind of backpedaling here. So we're not actually, because it turns out that there's different kinds of mixing. Okay, so in certain kinds of mixing of bits is helpful, and other kind of mixing is not. And the sorts of mixing that channels like ComCloud do naturally is not the kind of mixing that you want. Okay, so the kind of mixing that the ComCloud does naturally, it's very localized. Okay, so bits tend to get mixed with bits in their temporal vicinity. It's also very regular. You have the same impulse response that keeps getting convolved again and again and again. Okay, so very regular, very localized mixing. That's what the channel does naturally. Okay, it turns out what you want to achieve really good performance, okay, is you want mixing that's very irregular, and it needs to be long range. You don't just mix bits next to each other in the order in which you're sending them. Okay, you mix bits from totally different parts of the string together. Okay, that's the kind of mixing you want. So in practice, the way you achieve this is you first try to undo all the mixing the channel does, or encode it in such a way the mixing doesn't happen to begin with, so the channel doesn't do any of its mixing. Okay, and then on top of that, you do a certain kind of mixing that gives you better performance. Okay, and that's what coding is about. You all with me? Okay. So this idea of mixing bits in this kind of long range and erratic way is useful for all kinds of channels. It's useful for ComCloud. It's useful for y equals hx plus z type of channels. It's kind of hard to understand how it works and why it works in that kind of a channel. So I'm first going to explain this in a very kind of simple cartoonish channel that's not really very useful, okay, as a model for practical communication, but I think it makes it very clear why mixing is a good idea. Okay, so it just makes the phenomenon very transparent. And once we understand that, then we'll map it over to ComCloud. Okay. All right, so let me show you the channel that I have in mind. So it's called the binary erasure channel, often abbreviated BEC. Okay, so here's the channel. So ComCloud is a continuous amplitude channel, right? You feed in real numbers and you get out real numbers. Now we try to send bits over those real numbers, but the channel itself is sort of oblivious to the bits, right? It just samples go in, real numbers go in, real numbers come out. This channel is a binary input channel. So the input to the channel is a bit. The output is one symbol from this alphabet of size 3. Okay, and the channel operates as follows. If you feed in a 0, at the other end you observe either a 0 or this special symbol E, and we'll call it erasure. Likewise, if you send 1, you either get a 1 at the output or you get the special symbol E. Okay, and the channel is stochastic. If you send in a 0, you get 0 with probability 1 minus epsilon, and with epsilon you get erasure. And likewise, if you send a 1. Okay, so the way the channel works is the encoder feeds in a bit. Okay, the channel either eats it with probability epsilon and tells the decoder, I just ate your bit. Sorry. Or it passes it through with probability 1 minus epsilon. Okay? And the bits are, it eats the bits independently from bit to bit. So with each bit, it flips this coin, it decides whether to eat that bit or not, independently of the past ones. So let's do a quick example here to make sure we're on the same page. So suppose the input is 1, 0, 1. These are not necessarily the bits I'm transmitting. Okay, so they're not necessarily the data bits. Okay, so for the ComCloud, it's quite simple. You only have one set of bits, right? There's like the data bits you're trying to send, and the input and output to the channel are real numbers. Okay, here we're trying to send bits, but the input to the channel is also bits. So the encoder is mapping bits to bits, right? And the decoder is mapping like this elements from this ternary alphabet back to bits. So suppose you just feed in 1, 0, 1 into the channel. Okay, you get 8 different possible outputs, right? The channel can erase no bits. That happens with probability 1 minus epsilon cubed, right? It can erase just the first bit. That happens with probability epsilon 1 minus epsilon squared. It can erase just the second bit or just the last bit. Those also happen with probability epsilon times 1 minus epsilon squared. You can erase the first 2, you can erase the outer 2, or you can erase the last 2, or you can erase all of them. Okay, and all of these double erasures have probability epsilon squared 1 minus epsilon, and the probability that erases everything, epsilon cubed. Right? All right, sometimes people will motivate this channel with, sometimes people will try to modify, connect this channel to some physical phenomenon, like, where does this come up? Like in wireless situations, for instance, a common failure mode for a wireless system is that the transmitter sends a signal and it's at passband, so it's heavily sinusoidal, okay? And the signal kind of bounces off a bunch of reflectors, walls, buildings, mountains, the ground, whatever, okay? And those signals destructively interfere right at the decoder's antenna, and so the decoder just picks up nothing, okay? And the decoder can sense when it's picked up nothing, because it's just like received power level is just 0, okay? So if the encoder sends like, antipodal, a bit with antipodal signaling, then the decoder can sense either that it was plus 1%, a minus 1%, or just got nothing because it experienced this destructive interference. Okay, so in that case, you might model it like this. So either the bit gets through or it gets erased. Okay, that's one way of thinking about this channel. Sometimes people will consider, they call it the packet erasure channel. So rather than sending a bit that's erased, you send one of like m different values where m is really big. And the channel either sends the value through or it erases it. Okay, and that you can view as a channel for like packet transmission on the internet, like UDP packets. Okay, so you send a packet and either it gets through without error or the internet eats it. Okay, and then you're trying to communicate over a channel like that. Okay, so anyway, I mean there are situations you can argue are modeled by this channel. For us, this is just a pedagogical tool. Okay, this channel is simple, it's clean. Okay, phenomenon that occur for most channels also occur here, and they're often easier to see here because the channel is so clean and simple. The reason it's so clean and simple, by the way, is that like the decoder knows what it doesn't know in some sense. Like, if you receive this, it's like, okay, that was a 1, that was a 1, and that you don't know what that was, right? You can contrast that with what they call the binary symmetric channel. The BSC just flips with probability epsilon, right? So then, you get a bit string of the decoder, and some of the bits have been flipped and some aren't, and you don't know which are which, right? So, yeah, if I could make a Donald Rumsfeld joke, like this channel only has known unknowns, and this one has unknown unknowns. That joke used to really work in 2006 when I started at Cornell, and now, like, do you guys even know who Donald Rumsfeld is? No? Okay. Exactly, yes. You have a question?
So how come in the first channel is it not possible for a 0 to be incorrectly mapped to a 1 and a 1 to a 0?
I'm just decreeing it. This is the thing. So this is not. Don't think of this as like a naturally occurring. I probably shouldn't have even mentioned the wireless and internet thing. Like, I'd say don't even think of this as like a naturally occurring channel. Just humor me and say, suppose we had a channel that guaranteed it never flipped your bits, but it might eat some. Okay? And we're going to understand why mixing bits, I think it's going to be clear why mixing bits is a good idea when you're trying to communicate over that channel. And mixing bits is actually useful in all kinds of channels, but it's kind of harder to see it in other examples. It's like really clear in this case when we get to that. Yeah. Other questions? Okay. So let's talk about how to communicate over this channel. So consider a new problem now. Suppose this is our channel. Put ComCloud aside for a moment. Suppose that's your channel, and I want to communicate over it. And suppose we want to send k data bits over n samples or channel uses. I'll say samples. Okay, so it's like you get to use that channel n times. So you get to send n bits. Okay, and your goal is to send k data bits and have them be recovered at the other end. Okay? So again, like it's a little bit confusing because bits kind of arises in two ways here. There's the data bits you want to send. Okay, but then each input to the channel is also a bit. Okay, so the encoder is going to map k bits to n bits. Those go through the channel. The decoder will get a bit string with some e's in it, and then try to recover the k data bits, right? Okay, so how do we do this? By the way, let's set a parameter now. We're going to call k divided by n the rate. It's like bits per sample we're sending. Okay, so we send k data bits over n time steps, so k over n is the rate. Okay, so here's a question for you. Suppose we have feedback first. So suppose the encoder gets these k data bits, okay? Has to output kind of one bit at a time, which goes through the BEC. Okay. That goes into the decoder. The decoder at the end of the transmission will output the k data bits. Okay. And let's suppose for right now, okay, I'm going to make the problem even less realistic now. let's suppose the encoder can observe the outcome of each bit immediately after it happens before it sends the next bit. So I'll just draw it like this. Okay? So the encoder observes all k bits. Okay? From those k bits, it somehow crafts one bit to send. It sends that through the channel. Okay? It then observes whether the bit got through or not. And it knows that the channel won't flip it, but doesn't know whether it'll eat it or not. Okay, so it learns whether that channel got eaten or not, or whether that bit got eaten or not. Okay, it then decides what to send for the next bit. It learns whether that one got through or not. Does that n times. Okay, after n time steps, the encoder is done. The decoder then observes a string of length n, each symbol of which is either 0, 1, or e, and it tries to guess the k data bits. Okay? So what's a reasonable strategy for this? If you're the encoder? Yeah. Transform k into a, okay, so k is a bit, you have k bits. So I guess you could like interpret that as one big integer. And then what do I do?
You send it, and every time you send E, you send it again.
But I can only send one bit at a time.
Sure, so you send them in order.
So why do I need the integer then?
I guess you don't.
Okay.
Let's say this. Oh, no, it doesn't.
Okay. So people clear on the design here? So just keep sending. Each bit. Until it gets through, right? So take the first bit of the k, just keep hitting the channel with that bit until you see it got through. Then take the next bit from the k, just keep sending that until it gets through, keep going. All right? Okay, at time n, the music stops. You can't send any more bits at that point. The decoder has to guess the bit string. Okay? If you've gotten all the bits through, if you've gotten all k bits through in your n chances, then the decoder knows all the bits. So there's no risk of an error at that point. It can happen if there are too many erasures, like say if the channel erases everything. Okay, it can happen that not all the bits get through. In that case, the decoder has to guess some of the bits. All right? So we'll analyze the error probability for this next time. This does not involve mixing yet. I just keep sending one bit and then the other, right? We'll see, though, once you remove the feedback link, though, then suddenly mixing bits becomes very powerful. Okay? So that's where we're headed. All right, so I have office hours right now if you want to chat about Lab 3 or whatever else. And I'll see you Tuesday. Oh, and we have the prelims, too. So again, the scores are, the statistics are up there.